Now, let me give an overview of the Hilbert space. And before this video, I have talked about the inner product of the Hilbert space. So, what is Hilbert space? We can say that this Hilbert space it's a complete vector space. So, to generalize this, a Hilbert space is uh, is a complete vector space that's basically equipped with an inner product. And what it does basically, it provides the structure that's needed for quantum mechanics and the other areas of physics and mathematics. And so we would like to start with the properties of this Hilbert space. Now, the first important property is that it's a vector space. I mean, this Hilbert space is a vector space. And if we talk about addition, we can add vectors together. Suppose we have two vectors, vector u and vector v. We have these two vectors. Then we can add them. We can add these vectors, vector u plus vector v. And this addition of the two vectors is also a vector in the Hilbert space. The next important thing for this vector space is that we can multiply these vectors. We can multiply these vectors by scalars. So if I assume, say, for example, C is some kind of scalar, it's a number, we can multiply these vectors by scalars. And the vector will be modified in magnitude due to the scalar that has been introduced. So one thing is addition in the vector space. The next thing is the scalar multiplication. So I can say that on multiplying vectors by scalars, then now these scalars can be real numbers or they can be complex numbers. Now, if I assume that this u is a vector, which I have already assumed, and this c is a scalar, then this cu is also a vector in the Hilbert space. Now, the next thing is the inner product. So to say, so to talk about this inner product, we have the two vectors, the vector u and vector v. Their inner product is defined as uv. And this inner product is a function that takes two vectors. It has this inner product is taking two vectors here, and what it does, it returns a scalar. It measures what it measures. It measures the overlap of waves, wave function, whatever we may have. And this inner product has properties. It has a property of linearity, which we have already discussed in the last video. So if I take the inner product of alpha u plus beta, say I'll take w v. So this must be equal to alpha inner product of u v plus beta inner product of w v. The next important thing for the inner product is the symmetry. Now, symmetry is important here. Now, what does symmetry mean here? That if we have the inner product of u and v, this inner product must be equal to v and u complex conjugate. This bar is a representative of the complex conjugate. of of this inner product. And the third important thing that is essential for this inner product is the positivity. And what's that? If I have u and u, their inner product, this inner product will always be greater or equal to 0. And this inner product will be 0 only if the magnitude of u is 0. This inner product will be 0 only if the magnitude of u is 0. The next important property of this Hilbert space is completeness. The space is complete if every Cauchy sequence, I mean, if a sequence where the vector gets some arbitrary close to each other, or I should say that the space is complete when the vectors converge. They converge to a point within the space. So if all the vectors converge to the point within the space, what does it do? This ensures there are no missing vectors. There are no missing vectors. And if we take the examples, some simple examples of, let me take an example for inner product. What I have is, we have an example for which I define two state vectors. Say I define U. It's a vector of a column matrix U1 and U2. And we have V, a vector V1 and V2. Now, if we want to take the inner product of these two vectors, U and V, this will be simply U1 V1 plus U2 V2. Now, if I use some numbers, say U is 1 and 2, and V is 3 and 4. So we can find the inner product for these real numbers. What will be that? UV will give us, that will be 1 times 3 plus 2 times 4. That will be 3 plus 8, and that will give us 11. So we have taken the inner product of two state vectors, U and V. And these are real numbers that we have chosen here. Now, proceeding from here, let's talk about the quantum states as a vector, because the whole game is revolving around these quantum states, around these quantum vectors. In quantum mechanics, the state of a particle is basically represented by a vector known as, that we have been discussing, Hilbert space. And this state of the particle is often represented by a state vector, psi. Now, taking a simplistic example here, if I assume that I have a two-dimensional Hilbert space, so that psi is psi1 and psi2. While this psi1 and psi2, they are the complex numbers. And the physical meaning of psi is that it contains all the information about the quantum state of this system. The psi that we have, it contains all that information that it's dealing with the system. Now, we have another important property of this Hilbert space, and that is orthogonality. Orthogonality. And then at the same time we have orthonormal basis. Suppose we have two vectors, as we have been treating them as U and V, and their inner product is equal to 0. Now, if their inner product is equal to 0, what it means is that these two vectors are orthogonal to each other. And what orthogonality means in general, Orthogonality means the vectors are at right angle to each other. And if I put an example, say u is a vector 1, 0, and v is a vector 0, 1. I will calculate the inner product of u and v. So what that will give me? That will give me 1 times 0 plus 0 times 1, and that will give me 0. So what does that mean? That means u and v, they are orthogonal to each other. That means they are, the angle between these two vectors is equal to 90 degrees. Now, coming to orthonormal basis, if I assume, say if I assume that I have a set of EI, this set is an orthonormal basis if EI, the inner product of EI, EJ is equal to 0 for I not equal to J, and EI, EJ is equal to 1. Now, this is the condition of orthogonality, and this is the condition of normalization. So this is how we can interpret the orthonormal basis of a system. And if I take an example over here, I again look for the 2D space with two vectors, say E1 as 1, 0 and E2 as 0, 1. Now these are orthonormal bases. Any vector, if I have any vector, say psi, this psi can be represented as a column of psi 1 and psi 2. Now this vector can be expressed as psi 1 E1 plus psi 2 E2. Now, operators in Hilbert space. Now, talking about operators in Hilbert space. Operators are, what are operators? Operators are basically the functions. And what's their job? Their job is to map the vectors. They map vectors. They map vectors. Where they map them? They map them in the Hilbert space. They represent physical observables. What are the physical observables? They are position, momentum, and energy. Now, if I assume that there is an operator A, putting a cap on it, and write down this operator in terms of a matrix, say 2, 1, 0, 3. Now, applying, if I apply this A operator to a vector, I will apply this. I will apply this operator to a vector, say U. Let me choose the V. And what is V? V is V1 and V2. So operating this operator on this vector will give me 2, 1, 0, 3 and V1 and V2. So we can multiply them. So what we will get, this is 2V1 plus V2. This is 2V1, this is V2, and this is 0 plus thrice V2. So the result that we have obtained here is a matrix. Now, so this is the idea of using an operator on a state vector and obtaining some data out of it. Now, how it automatically leads to what we call as eigenvalues. The eigenstates automatically reach out to the calculation of eigenvalues. Now, what we have an operator A, and this operator A is acting on a state vector V. And what we obtain is lambda, and the state vector comes back. Well, this lambda is called eigenvalues. So, acting an operator on a state vector leads to the eigenvalues. Or I should say, the action of an operator on an eigenvector leads to the eigenvalues and the eigenvector. So if I take an example here, say I have a operator as 2, 0 and 0, 3. And let's try to calculate the eigenvalues and eigenvectors. And if I choose my v as the two state vectors x and y, so what we can do is we can use the eigenvalue equation, and we can calculate the eigenvalues. So what's that? So I have the operator 2, 0, 0, 3, and then x, y equals 2. Let's assume this lambda is 2. X, y. Now we can solve this, and solving this will give us 2x, 3y, that's clear from the multiplication, is equal to, this is 2x and 2y. So this is for lambda equal to 2. And if we take lambda equal to 3 here, what will we obtain for the same thing? We will obtain 2x, 3y is equal to 3x and 2y. Thus, what we say here, from this point of view, this y is 0. So if y is 0, what's the eigenvector then? Eigenvector is 1 and 0. For this, x is 0. Now if x is 0, what will be the eigenvector? The eigenvector will be 0 and 1. Now, another important property of Hilbert space is the superposition. It's the superposition and the measurement. Now, superposition and measurement. Now what we have, suppose we have a quantum state, and a quantum state can be expressed as a combination of basis states. And if I assume that psi is a state in Hilbert space with orthonormal bases E1 and E2, then psi can be written as a combination of AE1 plus BE2, where A and B, they can be complex coefficients, they can be real numbers. So this is the reflection of superposition. Now, when measuring an observable, when we have to measure it, the possible outcomes are the eigenvalues of the corresponding operator and the probability of each outcome. So the probability of each outcome is given by the squared magnitude of the coefficient in the superposition. And we can take a simple example for it. Suppose this psi is 0.6 E1 plus 0.8 E2. Now, the probability of measuring E1, the probability of measuring E1, what will be that? That will be 0.6 more whole square, and that will give me 0.36. And the probability of measuring of E2, that will be the square of the mod of square of 0 point whole square, 0.8. So this will be 0.64. And if you add the two probabilities, they will come out to be 1. So here what I have tried is I have tried to give an overview of Hilbert space. Hilbert space is it's a topic with endless boundaries. It cannot end at any point. But I have tried to give a miniature kind of expressions so that there is a view of understanding that was the reflection of this Hilbert space in quantum mechanics. So this Hilbert space, they are essential. These spaces are essential in quantum mechanics because they provide us a beautiful framework for describing the quantum states, for describing the observables, and carrying out the measurements. And we have the mathematical tools like the inner products, orthonormal bases, and operators. And what they do, they allow for a structured approach to the understanding and predicting quantum phenomena. So by using vectors to represent states and matrices as operators to represent the physical quantities, what we can do is we can make precise predictions. We can make precise predictions about the outcomes of the measurements and in general the behavior of the quantum systems.